Okay, so how is everyone today? Good, I hope? All right, so between last time and now, I've had time to look at the calendar. I was caught a little bit surprised. Are the lights, is this how the lights usually are? It is? Okay. Let's see, today is the 20-something or other, 21st. So I had time to look at the schedule and figure it out. So this is the revised plan for the midterm. So as a reminder, the midterm exam is Thursday. That's 7 days from now. Thursday. The 28th. No. Come on, brain. Get into gear. Thursday. That'll be the only thing that we do on Thursday. So then, we won't do any lectures or other stuff. Just the exam. Today, we're doing WEX, the 04 and WEX 05 quiz. So I'm going to grade this tonight and post it tomorrow. Graded and posted tomorrow. Then, what am I saying? WEX, like as was previously announced, WEX 06 and WEX 07. Those are due on Tuesday. Tuesday the 26th. Okay, so then that means that we're also going to do the WEX 06 and 07 quiz that day. And then I'm going to grade and post those immediately. So that night. And then, as a result, this is the change, is that those are going to be on the midterm exam. Now, you might think, a little bit panicked, and I can appreciate that, but just give me a second to explain. WEX 06 and WEX 07 will be on the midterm. What that means is that the midterm exam will still have about 5 new and mandatory exercises. And all that I mean by mandatory is just that all of them are going to be graded out of 10. And there will be 14 redo exercises. You can choose up to 7. Which is to say half of them. Now, I was thinking about what you said last time. You said something about all, and I was trying to think whenever did I say all? Okay, so then I think what I did say was something different, and that is that so like on the midterm we have these 14 14 out of 10 that you can redo up to 7. Then on the final exam, we'll play the same game. What I might have said all to is that all of the WEXs from the whole semester will be available for redo. And I'll agree to that. So what I mean is like, this is, on the order of half, because it's a midterm. I can appreciate that y'all might think that this is a short turnaround. But, in response, I say that, well, you get to try it on Tuesday. If it doesn't work, then you get to try it on Thursday. And if it doesn't work on Thursday, then you can try it on the final. So I think it'll be all right. But this will get us on schedule. And then finally, this week, WEXs, which is to say WEX 08 and WEX 09, they'll be due, not next week, they'll be due the Tuesday that follows the exam. So that's like the 3rd. All right. So I had to look at a calendar to get all that figured out, but there it is. Any questions about it? No questions? Okay, very good. Any questions before we get to new things? All right, let's get to it. So what we ended with last time was by parts. And so let's briefly remember what that was about, and then we're going to do a whole bunch of by parts exercises. All right. So, as a reminder, what biparts is well, it's the antidifferentiation technique that undoes the product rule. So, to remind you, if we say let u be a function of x and v a different function of x, so if that's the case, then just writing little d for differential, so d uv, well, the product rule would be that it's the differential of the first multiplied by the second plus the first one multiplied by the differential of the second. And then now we're going to solve for that one. Solve for that one right there. Doing that, we get u dv is, so that's moving that one over there, d uv minus du v. And then we can commute that product because product commutes, and anti-differentiate both sides so that we obtain antiderivative of u dv is antiderivative of d uv, and because antiderivative is homogeneous, it distributes across the subtraction to look like this. And then one more simplification can be done. What? Right. These two things are the opposites of each other, right? This one says do something and then undo it. So that's the same as doing nothing. So here we go. We have u dv is uv minus antiderivative v du. Okay, so that's a formula. It's a formula that we need to memorize. And the name for this formula is antidifferentiation by parts. Okay. So that's for antiderivatives. And then, we discussed the fundamental theorem of calculus, which tells you the intimate relationship between antiderivative and integral. So making this an integral statement. So now this u dv, now we'll say that it's an integral from a to b. And we need to modify somehow the right-hand side of this so that it's right. So pausing here for a second and just looking at what's written, this couldn't possibly be right because it doesn't make any sense. The reason why it doesn't make any sense is, remember that u and v are functions of x, right? So then in particular, the antiderivative here is a function of x, that's a function of x, that's a function of x, right? The kind of thing that the antiderivative outputs is a function of x. Whereas what is the kind of output of the integral? A number, right? So to make this equation make sense, like categorical sense, this has to somehow be a number, and that one also has to be a number, right? Not a function, but presently what they are is they're functions of x, but we need them to be numbers. All right. So the modification to this term, I think, is obvious enough. What do we need to do? Right. We need to say that this one is also integral from a to b. Okay. And then this one is, in my opinion, obvious when you think about it, but a little bit subtle, at least at first. So what do we need to do to this term? Not antiderivative. What do you mean? Right. So we need to do exactly the same thing that the integral would have done, which is to say, take that expression and evaluate it on the boundary, like so. So now this statement makes categorical sense in the sense that that's a number, that's a number, that's a number. Okay. So this one here is another formula. And it is called integration by parts. And I'm just going to refer to this general idea as just by parts, meaning antidifferentiation by parts when we happen to be antidifferentiating, and integration by parts when we happen to be integrating. All right. So standard example. So antiderivative of w multiplied by the exponential of w dw. So what antidifferentiation by parts is at least for us at the present time, it's step 4 in the Riesz procedure, right? Before antidifferentiation by parts, we just had 3 steps. So let's go through those 3 steps, which is to say, we're considering an antiderivative. Is this one of the ones that we know, like one of the ones that are of the blessed 3? Is it one of them? It is not. What's the second step? Yeah, can we do some kind of algebra, something or other? And lumped in here, is the things like, well, what if you're integrating and it turns out that you're integrating part of a circle, but that's not the case here. The third step is variable differential substitution. So can we perform a variable differential substitution? Nah, nothing's going to work. Nope. All right, so then, well, if it were not for antidifferentiation by parts, we'd have to say, I don't know, I have no idea. But here we go. So now we're going to check. Is it possible to do this in the by parts way? All right. So specifically, what we want to do is we want to consider that antiderivative of w exponential of w dw, and we want to consider it in the following kind of pattern: antiderivative of u dv. That is to say, the left-hand side of antidifferentiation by parts. So what we have to do is we have to figure out what we're going to consider to be u, and then by process of elimination, dv will be everything else. So the question right here we need to figure out is what is going to be u. All right. So I'm just going to say what's going to be u, and on this exercise, I'm not going to illustrate how it is that I made that choice. I'm going to do that immediately after. So for reasons that are not entirely clear, we're going to say that u is w, because in principle, u could have been the other thing, right? U could have been the exponential thing. But at any rate, having made the choice for u, dv is automatically everything else. Exponential of w dw. Okay, now here's the thing about the by parts formula. I'd like for you to observe that there's four things in the by parts formula. So in particular, we have u, that's the first thing, and dv, that's the second one. So besides u and dv, what else do we have? Well, there's another u. I don't need to count it again. But there's a v. Is that one new? Yeah, that's new because we had dv previously, which is a different thing. So then we have u, dv, v, that's a new thing. And then do we have anything other that's new? du, that's a new thing. So there's 4 items. And what I'm saying is that somehow I made this choice. I didn't explain how. But now that this choice is made, what can we get from u? So if this is right, then we can get du from that. Right? Because if this is u, how do we find du? Yeah, we just differentiate, right? So in particular, we know that du dw, well, what's the derivative of w with respect to w? 1. As a result, from this equation, du dw, what's u? Well, it's dw. du is dw. All right. Normally, when you get comfortable with this, you just skip that intermediate equation and go straight to the bottom one. I'm not sure I understand. Mm-hmm. Yeah, I mean, if what you're saying is a way to organize it in a way that makes sense to you, yeah, by all means, yeah. Okay, so here's dv. What can we get from dv? What can we figure out from dv? Well, what I mean is that we had u, and what do we find from u? We found du, right? And here I'm saying we have dv what are we going to find from dv? We're going to find v. So in particular, we could say, okay, v, that's the antiderivative of dv, right? And then, so that means that v needs to be the antiderivative of the exponential of w dw. And here's the thing. When you're doing by parts, when you're sort of checking it out, whether or not this is going to work, this is one of the moments of truth where you say, you know, is it going to work or is it not? Because if you can't do this one, then the answer is, you know, at least this attempt is going to fail, if it were not possible to do this one. So how about this one? Can we do it? Yeah, what is it? The exponential of w. So notably, at this position, there is no plus c yet. The reason why there's no plus c yet is because now we're going to plug in to the right-hand side of antidifferentiation by parts. So what I mean is that now it becomes uv minus the antiderivative of v du. Okay, so let's plug all those things in now. So uv, so w, multiplied by that, exponential of w, minus antiderivative of v, so exponential of w, du, which was dw. So notice that this is where the computation continues. So the fact that the computation continues and there's still an antiderivative, that's why that there's no plus c yet. There's no plus c yet because there's still antiderivative. So the plus c doesn't come in until that's all wrapped up. Okay, so now here's another, when you're doing antidifferentiation by parts, here's another moment of truth. So you have to pass this place where you say, okay, can I do that antiderivative? Okay, on this exercise the answer was yes. Okay, then we say, all right, then that would mean all that. And now we have another antiderivative, and this is another moment of truth. Can we do this one? And the answer on this one is yes. It can come to pass that the answer is no. But on this specific exercise, the answer is yes. So w exponential of w minus, of course, that's a known antiderivative, so exponential of w again, and then now plus c. But wait a minute. Literally like 8 centimeters away or something like that, I said no plus c. And now here I'm saying now you have to have a plus c. Okay, why? What's the distinction? Right, because now we're done. So now, because there's no more, antiderivative. All right. So now, that seems, in the first place, I hope that you have the impression that this seems kind of weird, right? Kind of like, I don't know. It doesn't really seem like that's really working. But, or, you know, you might be a little bit incredulous, which is to say that the previous exercise is making the statement w, antiderivative of w exponential of w dw, evidently is equal to w exponential of w minus exponential of w plus a constant. So that's what we're saying. Now how can we verify that this is in fact true? There's a relatively easy way to do it. Right. Because have a look. Have a look. What I want to do is that I want to rewrite an equation that has the equivalent content, that has the same meaning, but I want to make it to where instead of its antiderivative, I'm going to move that to the other side. Okay, so which is to say that if I leave w exponential of w on its side, and I leave w exponential of w minus exponential of w plus a constant on its side. And I want the operation to change signs. Then when antiderivative changes sides, what does it become on the other side? So it's antiderivative with respect to w on the left, and it's derivative with respect to w on the right. So, which is to say that this when it changes sides, you know, it morphs into a butterfly and becomes derivative, like that. So now that's something that we can actually check. So let's check it. So this will be the derivative. Of course, the derivative is additive. So it distributes across that. So we'll have the derivative of w exponential of w, like so, and then minus the derivative of the exponential of w, and then plus the derivative of c. Okay, so right to left is easiness. So what's the derivative of c? 0. What's the derivative of exponential of w? Exponential of w. Okay, and what derivative rule will we have to use to calculate the derivative of this product? The product rule, right? Okay, good. Aptly named. So then this will be the derivative with respect to w of w, and then multiplied by exponential of w, which is to say the derivative of the first thing multiplied by the second, and then plus the first thing multiplied by the derivative of the second one. All right. Well, what's the derivative of w with respect to w? 1. So this would be 1 exponential w, and then plus w, and the derivative of exponential of w is exponential of w, and then minus exponential of w, and then I won't bother writing plus 0. And then do you observe that, these cancel? Those two things cancel. So what are we left with? With w exponential of w. But that's what we wanted to show, right? So what the biparts thing is doing is it's doing. We just did this just now, you know, going top to bottom. What the biparts thing is doing is just going from bottom to top. That's what it's doing. All right. And as it, as it happens, in general, processes can be reversed, but the derivative direction is easier. It's kind of, you could think of it like the downhill direction. That's the thing that's easy to do, right? So like anybody can walk up a hill or down a hill, but going downhill is easier. Anybody can swim downstream or upstream, but going downstream is easier. That's why the biparts thing is a little bit, you can kind of think of it like that. Biparts is more complicated in that kind of way. All right, so now, here's the thing. How are we going to, how do we choose u? So how to choose u and dv in by parts. Okay. So then this is how to choose u. So you label non-differential factor now, to make sure that you take my meaning, that means i.e. Everything, everything except, every factor except the dx, or whatever the variable happens to be, with the following labels. As appropriate. So label it with an L if it's a logarithm of any kind, like natural log of x, log base 10 of w, or what have you, those kinds of things. Label it with an A if it's algebraic. So algebraic things are things like constants, things like polynomials, even terms that have a negative exponent, like x to negative 5, say, something like that, or square roots, things like that. And label it with an E if it's exponential. So, e to x, e to 8x, 2 to x, things like that. Okay, then you choose whichever one is highest, right? So if you find an L, then that's going to be you. If it's a choice between an A and an E, you choose A, etc. And then 2, dv is everything else. Okay. So now, when you read these instructions, I think it's conceivable that you could say, wait, there's a little bit of an ambiguity. What if I find like 2 L's? Then which one? And the answer is that that's a good question. But in the end, I'm never going to give you a question like that. So that's kind of an unsatisfying response, just to say that I'm going to keep us in a walled garden where that never happens. But, well, in the end, the world is a little bit bigger than this. Like the fact that we don't have trigonometric functions, we don't talk about them in here. The actual acronym that is typically used is not LAE. It's a little bit longer, and there's more choices, and it's a little more varied. But we're just avoiding all that complication. Good. So, by way of example, looking at the previous one, we were considering w times the exponential of w dw. And we went down the Riesz procedure and said, well, the first 3 steps are no-goes. It's not going to work, the first 3 steps. So then let's make an attempt for by parts. So now, using this rule, let's do it. So there's 3 factors in here, 1, 2, 3, but the by parts heuristic is saying that we don't deal with the differential bit. We just deal with the parts that aren't the differential. So then here's a w. We need to label it according to its category. What's its category? It's an algebraic thing. polynomial kind of thing, right? So it's an a. And then the exponential of w, that's an e. Okay, and there's no other factors. So that means that the choice for you, it's a contest between an a and an e. So who wins? The a wins. So we say, well, therefore, u is going to be w, because a was the winner, and dv is everything else. So I've written something. So is that right, what I have written there? No, it's not right. Why is it not right? Because you need to write the dw. So in particular, well, there's a couple things. And so in the first place, the rule is dv is everything else, right? So including that bit. On the other hand, if you write a math sentence that looks like that, dv is exponential of w, well, to the grader, it's going to seem like nonsense, right? Because in the end, the kind of thing that this is the kind of thing that it is. The category of it is a differential, whereas the category of this thing is a function. And to say that a differential is equal to a function is like high-grade nonsense to someone who's a young math graduate student who thinks these things are really important. So now this makes sense, right? Because it's saying that this thing, which is its category, its kind, is a differential equal to this other thing, which is also a differential. So what I'm saying is that makes categorical sense, and that bit there is not optional. I'm kind of stressing that a little bit hard in the end because I graded last night, and not many, but at any rate, there were several of you who tried to do a variable differential substitution and didn't write the differential part, and as a result, didn't even write anything about it at all. So it just looked kind of weird. Good. Any question about why? So we're not going to redo this one because it's on the previous page. I just wanted to revisit this one to show you, oh, that's why I made the choice u is w. Okay, so let's do another one, and y'all can make the choice about what u is going to be. Okay, how about the antiderivative of 3m plus 2 multiplied by the exponential of 4m dm.
Are we supposed to write this down, or do you want to?
Yeah, I want you to give it a go.
Oh, okay.
Because I kind of consider teaching to some extent like a performance art, a little bit, but I'd like for you to, be part of it. I'm sorry?
What is non-differential?
So are you asking about label each non-differential factor?
Yeah.
Well, so what I mean is i.e. everything except the dx, right? So you don't label that. That doesn't get a categorization. So, if you're having trouble getting started, that's okay. But let me sort of like give you some insight into human psychology. Well, just maybe generally animal psychology. So if you haven't had the pleasure of growing up on a farm with animals, or have experience with that, you might not be familiar with the phrase like a cow looking at a new gate. That's a phrase that doesn't really make a lot of sense in a city. But at any rate, what that means is that when you're taking care of cows, you got to keep them in a fence, right? Otherwise, they get loose. Sometimes it comes to pass that in the management of the farm, you've got to build a new gate in the fence. And what happens inevitably is that the cows, they all like huddle around it and they just stare at it for like a day. Like, they're like not eating. They just look at it. You're like, you gotta say, go on, get out of here. Go do something. Okay. Another matter is that one of the tricks of being a good teacher, like you can fake your way a lot using the following kind of technique. You say like someone can ask you a question. You say, oh, well, could you draw me a picture? Or could you just keep asking them, can you say it a different way? And then the point of doing that is that getting them to say it makes them hear it, which engages their auditory part of their brain, or getting them to draw something engages the visual part of their brain. So here's the thing. I'm trying to prod you on and say, come on, quit looking at it. Come on. And I want you to write something down. So the way that we do all antiderivatives is by procedure, right? So if you're having trouble getting started, just write it down, because it'll probably start calling up memories. So in the first place, is this one of the known antiderivatives? So is it in the list? It's not in the list. All right, so that step's done. Can we do something algebraic? Well, we can do a little bit, but let's see if it's going to help at all. So in particular, we could write this as 3m exponential of 4m and then plus 2 exponential of 4m dm. And, well, that's a little bit of a help, right? Because we could do that one. We could do that one immediately. We can't do that one. So why can we do that one immediately? Well, I mean, the multiply by 2 does nothing because the antiderivative is homogeneous, right? So you can essentially ignore that one, ignore the multiply by 2. And then the question becomes do you know the antiderivative of exponential of 4m dm? And the answer is yeah. Because remember that of the blessed 3, we usually write it like this, the exponential like this. But you've got to remember that that's a stand-in for like a family of things that we know. So specifically, we know the exponential of, in fact, any constant. So I'll just write a k for constant, kx dx. So we can do that one, and that's the exponential of kx over k plus c. So what I'm saying is that this one is in that one. So we can do this algebra thing, like we can do this one part and set it aside and just focus on that one. That's a fine way to go. Or if you, but we can't do the same thing for that one. That's not going to work because that's an m. Or we can ignore that. So what do y'all want to do? Y'all want to stick with this, or you want to ignore it? Ignore it? Okay. Maybe but we'll set that to the side and maybe come back to it if it's if we have to. What's the next step? Can we do a variable differential substitution? All right. Well, what do you think? No? Maybe? Okay. I'm not going to write u only because we might want to use u later. So I'm going to write a p. How about that? That's a good name. P is 4m. So we're just considering, whether or not we want this to be the variable in a variable differential substitution. So what else besides the variable? What else is that? What is it that we would need? Well, we'd also need the differential, right? dpdm, right? So then, in particular, can you do it without the intermediate step? What would dp be? 4 dm. Okay, so does that help? Not really, I think. Because looking to my eye, anyhow, it doesn't look like that's going to get us anywhere. All right, so maybe the answer is no to this one. So the next step, let's try by parts. So all that I meant by the new gate thing, okay, and the visual thing, is that every time I teach calculus, what happens is that a student will take a midterm or a quiz or something, and it is usually the case that in my estimation the student is entirely capable, but they'll submit like a blank response to a question like this, like blank. And then every time I ask, I say, what were you doing? And they say, well, I was just trying to think about it. And that's not what I'm telling you is that that's not a good strategy, right? It's not a good strategy because you are, by failing to write anything down, you're failing to fully engage your brain entirely against the problem at hand. What I'm telling you is that because what goes on, I say, well, if you were just following procedure, like if you were trying to teach this to someone else, if you were trying to teach me, what would you say? And I just have them, they just start writing it down, and then they write it down, and about 10 seconds later they say, oh, every time, right? Not every time, but very often. Okay, so all that I want to impart is just, don't have that be you. Just go ahead and write something down, and see if that will work for you. All right, by parts. If we're going to do that, that means we need to take this antiderivative, 3m plus 2, exponential of 4m, dm, and to go ahead with the by parts formula, what we need to do is we need to label all the non-differential parts, all the non-differential factors. So how about that factor? What kind of thing is that? This is algebraic. And what kind of thing is this one? Exponential. Okay, so then who wins? The algebra one. Okay, good. Now, so that means the algebra one wins, so who's going to be the algebra one? You. Okay, but for reasons that aren't entirely clear, I'm going to write you, and I'm going to put a little party hat on it. Only because I want to, well, it'll become clear when it happens. But for some reason, I'm putting a party hat on it. There's nothing significant about it right now. Fine, so then 3m plus 2. And then, if u has a party hat, then so does v needs a party hat, right? So then what's dv? Very good. E to 4m dm. Okay, so then how many items do we need to identify to be able to apply by parts? Correct. How many of them do we currently have? All right. From this one, what can we get? We can get du. So du is what then? 3dm. And from dv, what can we get? We can get v. So v is the antiderivative of the exponential of 4m dm. And so now here is the first moment of truth when you're checking by parts. Can you do this one? Okay, on this one the answer is yes. So then the answer would be what? Uh-huh. Divide by 4. Good. Do we do a plus c?
Yes.
Not yet, right? So not yet. No plus c yet. The reason is because we're going to take these 4 things and use them in the by-parts formula. So in particular, the right-hand side of the by-parts formula is uv minus antiderivative v du. And the fact that there's still antiderivative means that we don't have the plus c yet. So the plus c only shows up when the antiderivative is finally complete. So when there's no more of the s's. So then plugging in all that stuff there, so that'd be u v minus antiderivative of v du. Okay. So now this is the second moment of truth in the by-parts technique. So here we have a second antiderivative. And if we can't do this one, then it's not going to work. All right? So can we do this one? We can. How can we do it? Right. Because that multiplication by 3, that can be factored out. And so can that division by 4. So really, all what these represent, right, exactly. This is just like a 3/4. So the question really is, can we do that one? And the answer is yes. All right. So 3m plus 2 multiplied by the exponential of 4m over 4. And then minus, for that one, exponential of 4m over 4 times 3, and then plus a constant. Why plus a constant? Right, because that thing is finally, exactly, they've all been spent. Yet, there's still a problem actually on this line here. Something's not right. What's not right? I have a 3. Right. So here's the thing. That division by 4 was already there, right? And when we do just that part, we get another division by 4, right?
So we need to keep the original 3/4.
Right. So well, I'll simplify it a little bit, but now it's right. Because now there's 2 4s down there. Okay. In the end, the reason why I point that out is that this particular kind of error, it would be just fine if you had written it. Let me start again. It sounds like you probably would have written it like this.
Yeah, that's all I'm good.
And that would be just fine. There's nothing wrong with that. All that I mean to say and point out is that I find it to be the case that when students are given that particular kind of antiderivative, that the existing division by 4 seems to like cause some kind of brain cramp or something, and it gets lost.
That would just be 1/4, 1/4.
Mm-hmm. So here's the first one, the one that was already there, and that's the new one.
So if we write it like the bottom one, that's okay.
Yeah, it's just fine. All that I mean is that I find that a common answer is that one, without the red 2. That's all that I'm trying to say. For reasons that aren't entirely clear to me. I think it's just because that 4 is already there and it kind of messes things up in the mind somehow. Good. Any question about this one? So I guess we didn't need to, save that, and we didn't end up using it. Okay, good. Yeah? We're coming to it, but we're about maybe 15 minutes away from it. I wanted to get that in early, so that it can stew for a little bit. All right. How about this one? The antiderivative of, how about, what do I want here? Yeah, 12z times the exponential of 3z squared, like this, dz. Yeah. In fact, yeah, that'll work. Yeah, that'll be fine. Okay, so now, if you were going to make the kind of error that I expect you to make, you would have made it by now. Here's the thing, is that if you tried to use integration by parts, then you've made a mistake. You've made a mistake. So, well, the applicable, folk psychology is that, when what you have in your hand is a hammer, everything looks like a nail, right? Which is to say that, just because I just gave you the by parts tool doesn't mean that in all circumstances you're going to now use by parts.
Yeah, you can.
Yeah?
Use the by part to solve anything, to solve every single one.
Not really, no.
So for every single problem, there's like a different technique you can use.
For every problem, you start at the top of the reach procedure.
Oh, okay.
That's what I'm trying to. That's what I'm trying to get you. It's the third one, not the fourth one. You don't even get to step 4. So we ask, is this a known one? No. Is there something algebraic we can do? That 12? Yeah, I make no argument. I agree, but that doesn't get us anywhere. That the 12 can come out, no doubt.
So the fourth one, you couldn't just use it? I mean, even though it looks very similar to the other problem, you couldn't just use by parts?
But you get the wrong answer.
No, you won't get the wrong answer. It'll just be impossible. Because let's consider, if you were going to use by parts, let's just make an aside. But this is an aside, but understand that the purpose of me giving this exercise is for you to make a false attempt, an incorrect attempt to try to use by parts. That's the whole point of doing this one. So suppose that you bit and you try to do it. If you did bite and you tried to, force this to be a by parts, to try to do this by parts, then, what would you say is u? 12z. Because that's the algebraic part. And what would you say is dv?
E to the 3z squared.
Exponential of 3z squared dz. And how many items are there in the by parts formula? 4. Here, we're offering up these two. Now, from this one, we can obtain that du would be 12 dz. So that's easy enough. And then the question becomes, okay, v needs to be the antiderivative of this one. And here's the thing about that antiderivative, is that you can't do it. Which one would it, how would you do it? Oh no. Oh no. No, I think you're misunderstanding me. I don't mean like you personally don't know how to do it. I mean that it's I mean that it's not something that's done. Right? It's not doable. Can't be done. Okay, so I agree that it looks let's look at this is even more of an aside. So what if we just consider this? Get rid of that constant and look at this. E to the exponential of x squared dx. Just getting rid of that 3. And then ask, can we use the exponential rule for it? We cannot. We cannot. Because in the end, in order to use the exponential rule, it has to be the case that the argument to the exponential and the argument to the differential have to be precisely the same. Are they the same thing? They're not. That's an x squared, and that's an x. They're not the same. If they were both just x's, it would work. If they were both w's, it would work. If they were both bananas, it would work. But they're not. So it doesn't work. The things in the red boxes have to be identical. Like you've got square root, and then you've got the thing that you want to put into the square root. So like the thing that you put into the other thing, the math word for thing that put into the thing is argument. Okay. So the argument of the exponential, which is to say that bit, has to be the same as the argument to the differential. Okay, so this won't work. All right. So at any rate, going back to this one, is this a known antiderivative? It is not. It's not one of the blessed 3. Is there something algebraic we can do to sort of like massage it into one of those 3? No, though I make no dispute that the 12 can come out. The next step is, can we do a variable differential substitution? Well, can we? And now the answer is yes. So what if we say like h is 3z squared? Meaning that we're offering a variable differential substitution and this as the variable. So what else do we need to do? dh, right? So then dh would be what? Six z dz. So that's the differential part. And then making a copy of the antiderivative down here for me to just look at here, I'm going to help myself a little bit. Since the differential part seems to be something that looks like that, I'm going to write that stuff over there on the other side so that it looks like this. Exponential of 3z squared, and then 12 z dz. All right. Well, I could take this 6 and divide and say something like this. dh over 6 is z dz. So what we'd be offering is to say, that this h here is gonna be this, and this dh over 6 here is going to be this. So will it work? It will, right? Because in a variable differential substitution, all you have to do is substitute all variables in differentials. Like, it might be a little bit concerning that we didn't cover the 12, but yeah, it's neither variable nor differential. So it need not be concerned, or like he said, we could just factor the 12 out at the beginning. Right, yes, yes. So, okay, good. So then I'll continue. So then doing this, it becomes antiderivative exponential of h, multiply 12, and then dh by 6. And then, yes, as you say, the 12 over 6 is a 2, which can come out. And then just imagining it to have already been taken out, what's the antiderivative of exponential of h dh? Exponential of h. So it's a constant. And then is this the answer to the question? What do you mean? No. No, it doesn't need to be divided by h because remember the rule is that we have this one.
That's only if there's a constant.
Right. So exponential of x like this, and then part of this family is that what if it's instead of just 1x, what if it's like 3x, something like that? In that case, then it's the exponential of 3x over 3 plus a constant. So in this case, the h's are in agreement. So then, nevertheless, my question stands. Is this the answer to the question, to the exercise?
No.
It is not?
Well, h.
Right. We have to get back to z's. So 2 exponential of 3z squared plus a constant. Any question about this one? Again, the point of throwing this one in there is just to remind you that, yes, by parts is a new, shiny new thing, but you still know other things. All right. How about this one? The antiderivative of the logarithm of t dt. Is it? So that's the first question, right? It's always the first question. Is this one of the blessed three? Is it? Let's write them down. What are the ones that we know? Well, let me back up. If whenever I set this particular question or a question like it as an exercise, a very common wrong answer. So very common incorrect answer answer is they'll say that this is equal antiderivative of logarithm of t dt. The response will be something like 1 over t plus a constant. So if you're copying what I'm writing in red, please note that it's not right. Nevertheless, I'm letting you know that this is a very common wrong answer. So let's see if you can put your finger on what how a student might come to this. So the ones that we do know, we know the antiderivative of x to n dx when n is not -1. We know that one. That one is called the power rule, and this is the answer. So anything that looks like x to n, except n is -1, we can do. And then we can also fill the hole when n is -1. The specific case, antiderivative of x to -1 dx, that's the logarithm rule. Logarithm absolute x plus a constant. And then we have this one, the exponential rule. But the thing is that there's another way to write x to -1. What's another way to write x to -1? 1 over x. So that this rule could be written in this way. The antiderivative of 1 over x dx is logarithm absolute x plus a constant. So now,
It's the differentiation.
yeah. Yeah, I mean, you know, the derivative of logarithm of t is 1 over t. Or you could think of it like this is the correct rule, but a student who makes this response has sort of like transposed those two bits. Okay. So, is this a known antiderivative? It is not. 2. What's the next step? Can we do something algebraic?
I mean, I did to fix my mistake.
I'm sorry?
I did to fix my mistake. Like, I made an imaginary 1, and I took that out.
Okay, all right.
Like, I took the 1 out so that I could make, v prime equal 1, because you're multiplying like ln t and dt.
Okay, I think I see where you're going, but my question right now is that is there anything algebraic we can do? In the end, the question of is there anything algebraic we can do means that is there something that involves purely algebraic steps that turns the antiderivative in question to one or more of the things that we know? Okay, there's no purely algebraic steps that we can do. Okay. How about a variable differential substitution? I mean, well, let's give it a go. You know, how about you know, I don't know. What's a letter that we haven't used? Y. What about I don't know, like y is the logarithm of t or something. So if we try that, and that's going to be the variable, then what else do we need? We'd need the differential, right? So dy would be 1 over t dt. Do we have a 1 over t hanging around that can, no? Okay. Finally, if this variable differential substitution is not going to work, can we do it by parts? Okay, now, I'll have you want you to think about it for a second. And if you're having difficulty seeing what to do, don't worry. There's a slight trick, which it sounds like maybe you can see. But if it's kind of hard to see it unless someone's shown it to you the first time. But it's kind of obvious after that. So if we're going to do by parts, we need to label stuff. Okay, so yeah, the hint, if you're having a problem looking at it, is you could say, well, isn't that the same as this? Sure, yeah. But really, you could do it even without it, right? Because either way, considering either one of these, is that let's label all the bits. So then, if we label this thing, what's this? Yeah, but what I mean is in the categorization. That's an algebraic thing. That belongs to the algebraic category. And then what kind of thing is that? That's a logarithm. So between those two, who's the winner? Logarithm. Alternatively, if we label this factor, what kind of thing is it? A log. And then that's the only one that ran the race. So who's the winner? That one, right? So that means who's u? The log. Okay, good. In either way, log is u is the log. So u is log, and as a result, what's dv? dt. Everything else. And then there's 4 items in the biparts formula. We have 2 of them. And from these 2, we can find the other 2. What can we find from du? From u? du. So then in particular, what is du? One over t, dt, right? The dt is not an optional part. And then what can we find from dv? We can find v. So v must be the antiderivative of dt. And what's that? Not quite. Antiderivative of dt. Not a constant. It's not. It's definitely not x. But you're getting closer. T. There you go. It's got to be a t, right? Which is probably what you meant when you said x. So, well, in the end, the reason is because, what's the derivative with respect to t of t? It's 1, right? In particular, dv is 1 dt. Do we do a plus c here? Not yet, because we're not finished. So now we need to plug this into the right-hand side of the biparts formula. And I'll write it down again and say it again. U v minus antiderivative v du. Because, in teaching, especially something like math, besides being correct, which is of course important, the next most important thing is to repeat yourself. And then after that, the next most important thing is to repeat yourself. So I'm saying this as many times as I can. Now I plug this in. Logarithm of t times t minus antiderivative of v, so which is t, and then du, 1 over t dt. So now, whether or not we're going to succeed with biparts hinges on whether or not we can do this particular antiderivative. So can we do this one? Well, I mean, yeah, so let's think about it. Let's just go to the top of the procedure, right? So for this particular one, is it known? No, that's not, if you just go consult the list, this one is not exactly one of the ones in the list. Then is there something algebraic we can... Yeah, is there something algebraic we can do? Can we algebraically simplify something? Yeah, right? The t over t cancels. Okay, well, let's do that. So this would be the logarithm of t times t, and then minus the antiderivative of the t's cancel, and then we have dt. Oh, yeah. So now let's look at that one. Can we do that one? Well, why does 3 over 3 cancel?
It's basically the same thing, just putting it, because it's multiplied, so you can just shift it up to the 1 next to the 1.
Right, right, exactly. This is like 5 times 1 over 5.
So it's not canceled, but it's like theoretically 1.
Yeah, yeah, they cancel to 1. They multiplicatively cancel, not additively cancel.
So they're not really canceled, but they're times 1.
Okay, yeah, let's say it like that then. So then for this one, is this one of the ones we can do? Yeah. So what is the antiderivative there? T. So logarithm t, multiply t, subtract t, and now finally plus a constant. Any question about this one? This one is okay? All right. Good. What about the antiderivative of the logarithm of, let's think here. Let's put something fun in there. So how about, no, not too fun. How about 13 x squared, yeah, 13x squared plus 26. That'll be fun. And then I want to say that this is what? If I say, oh, come on, brain, get into gear. I need to write over here. My brain is like I'm having a brain cramp. Yeah, it's what I thought it was, but then I was hesitating for some reason. Huh. Must be suffering from exhaustion. Okay, so then I'll put an x here like that, and then a 13x squared plus 26 there like that. Then dx. Beautiful. All right. So what do you think? Yeah?
If there's a term like that where ln is in front of the, is there something special like that where you can't just cancel the 13x squared? Like, does ln have to stick to the?
Yeah, it sticks to it.
Okay.
Yeah, yeah. I think I take your meaning is that you can't. Well, I agree that that's a 13x squared plus 26 there, and also 1 there.
Right.
But this one that's inside of the argument, that's the argument of the log, cannot come out to play.
Okay.
So it can't cancel with this one. What do you think? By parts? Okay, why do you come to that conclusion? What takes you there? I'm sorry?
That looks kind of like the example you did before,
It looks like the one we did before?
except with more ugly numbers.
More ugly numbers. Okay, well, I mean, in the end, what I'm trying to get y'all to do is I'm trying to get y'all to see that there's like literally a procedure that we go through. So, the first step, is this one of the known ones? No, it's not. Can we do some kind of algebraic something or other? Not really. In the end, more or less, because the only kind of entertaining thing that you could do is if the logarithm could distribute across the sum, or if this could somehow come out, but it can't. So there's nothing algebraic we can do. What's the next step? Yeah, now let's try a variable differential substitution. Okay, so if you went immediately to by parts, then you're guilty again of biting, taking the bait. So you've got to exhaust this one. You've got to figure out, can you do this or can you not? And the only real way, well, not the only real way, but honestly, the most time-efficient way is just to write it down and try it. So what do you want to try? Okay, use this one, 13x squared plus 26. So if we do that, then what would du be? Okay, 26x dx. Well, notice that we have that x. So what I mean to say is, you could look at this you could look at this in this way. Antiderivative of logarithm of 13x squared plus 26 over 13x squared plus 26 and then x dx. Right? Okay. So we could take that 26, which would be extra, and we could say du over 26 is x dx. So suppose we do that. Suppose we do that. What all would we cover if we did this substitution? It would cover the argument to the log. What else? It would also cover the denominator. We'd have to put a u there and a u there. That's okay. What else could we cover? Right? So do you see that that covers everything? It does. So let's do it. They are, but they're the same thing. They're both they're both 13x squared plus 26. They can't algebraically intermix because one of them is stuck inside of the log, so it's like inside a cave, can't come out.
But they can be represented by the same letter, like you.
Absolutely, yeah. So if we do that, then the new thing would become antiderivative of logarithm of u over u, and then that becomes du over 26. Okay. So the division by 26, that can just come out, right? Because that's a constant. And now here's the thing, is that, this u in the denominator, for the purposes of calculus, there's a nicer way to write this. Yeah, so let's write it like this. Let's say that this is I'll factor out the 1 over 26, and now it's a logarithm of u, and then u to negative 1 du. Now what? I'm sorry? I'm not sure. I don't understand what you mean.
You can't.
But you can't do them like piecemeal, because they're all multiplied together.
What if now you use my
Okay. Well, let's back up a little bit. Let me write one other representation. At any rate, this one looks significantly different than the one we started with, right? So then every time it comes to a place where it looks significantly different, that means that now it's time to start back at the top of the procedure. All right. So now is this one known? Nope. Can we do something algebraic? No? Can we do a variable differential substitution? What?
Maybe y equal L.
Yeah. Y is the log of u. Because if this is going to be the variable, again, right, up here, that was the variable that we put on offer, and this is the differential. What we're saying is that now we're putting this differential on offer. What's its corresponding, sorry, this is the variable we're putting on offer. What's the corresponding differential? dy would be what? One over u du? Does that cover everything? So we'd be saying that this is going to be y, right? And this is going to be dy. So did we cover everything? We did. All right. So then that would mean that the new antiderivative looks like this. Antiderivative of y dy. Okay. Is this one of the antiderivatives we know? Oh, it is. Okay. So the answer would be what? 1 over 26 and then what? Very good. Y squared over 2 and then plus a constant. And then is this the answer to the question? No, because we need to get back to u's. So this would be 1 over 26 times, now it'll be logarithm of u squared over 2 plus c. Now is that the answer? No, because we need to get back to whatever we started with, x's. So this will be 1 over 26 logarithm of 13x squared. Y is what one? The one above?
Yeah.
Well, because the symbol in that exercise in that line is u. But what symbol was the question phrased in? In x, right? So now we're back to x.
Oh, okay. So you just
From x's to u's, from u's to y's, and then y's to u's, and u's to
go back
x's.
to the original.
Yeah, to the original one. Now, we did it with 2 substitutions. In your own time, because we don't have time to do it here, you might try, instead of trying to do it in 2, convince yourself that you could have done it with 1 substitution. You could have said w is the logarithm of 13x squared plus 26. So that would be the variable. And then try to consider what the differential would be that corresponds to it. And you could have, we could have done these 2 substitutions, these 2 separate ones. We could have done it like all with one big swipe. Good. Any question about this one? Okay. So the last thing that we need to do today is one of these. Notice that, you know, at the beginning we said that there's 2 techniques. One of them is antidifferentiation by parts, and the other one, integration by parts. So now, obviously, if this is going to use any by parts of any sort, it's definitely going to have to be integration by parts because this is an integral. Okay. So in the interest of time, I'm going to skip the formalities and say, yes, we're going to just have to do it. So in particular, what I mean is we're going to have to do by parts because none of the other three things are going to work. So in particular, we're looking at it like so. So I wrote, instead of write divide by x squared, I'm writing multiply by x to exponent negative 2. And this one almost kind of looks like the previous one, right? In fact, it's like, you know, if we ignore the limits for a moment, then it's like almost identical with the exception that the previous one, that exponent was negative 1. Right? But now it's negative 2. So will we be able to do substitutions with this one? And the answer is going to be no. In the end, we could do a substitution if that was negative 1, but it's not. So we're going to have to do by parts. Let's label the individual pieces. What's the label for this one? Good. And what's the label for this piece, this factor? Not exponential. It's algebraic. To be exponential, it has to be a constant base with a variable exponent. But that exponent is negative 2, which is not a variable. Like 2 to x would work, yeah. Okay, so between these two runners, who wins the race? Log does. So then u would be logarithm of x. dv would be everything else. Oh, you know what? I forgot to. Darn. I forgot to. I'll do it next week maybe. I forgot to do the one where the hat thingy would have. But now I've run out of time. It doesn't matter. You can just ignore the hat thingy for now. Fine. So then this will be from u we can find du. So du would be 1 over x dx, and from v we can find dv. From dv we can find v. So what's the antiderivative of x to negative 2 dx? X to negative 1, divide by negative 1. That's the power rule. You increase the exponent by 1 and divide by the new exponent. No plus c because we're not finished yet. So doing that, this will be, so we write u times v, so u times v, and then what do we have to do with this u times v? You evaluate it. You do the boundary evaluation, the same thing that you do with the fundamental theorem. So this from 1 to e, like so. Okay, then subtract integral 1 to e of now v du. So v and then du. So now all this needs to be simplified. Well, that needs to be evaluated, and all this stands some simplification. All right, so in the first place, because this over here, this evaluation, this is algebraic, that means that a nicer way to write x to negative 1 is what? 1 over x, right? So that's over here because we're doing like an evaluation. But over here, writing this 1 over x, what's a nicer way to write this 1 over x? X to negative 1. Right? Furthermore, this negative, because this is division by negative 1, that's just a regular old negative, and it'll cancel with that negative, right? Okay, good. So I'm going to make a few simplifications. So this will be what? Negative logarithm of x, and then I'll write over x like that. This still from 1 to e. I haven't done anything, just made a simplification there. These negations cancel so that we have plus integral 1 to e. And then how can we simplify these x's? What do they become? Can you see it? Not quite. So, well, okay, we'll do it like that. So we could say this x to negative 1 could also be written like this, 1 over x, and then that one also like that. See? So if we do it that way, then that would be written as 1 over x squared. But for the purposes of calculus, what's a better way to write 1 over x squared? X with exponent negative 2. So that's where the 2 came from. That's where the 2 goes. Also, so plus, again, we're just sort of like gearing up. I haven't done any calculus yet. I'm just getting ready to. So from here, we're going to be able to use the fundamental theorem. Now I'm going to do one more thing because it is a little helpful, a neat little trick, and that is well, when you do the boundary evaluation, you know it's the one thing minus the other thing, right? But whenever this thing has a negative, I find that students usually, well, not usually, but at any rate, often kind of mess that part up. So here's a nice way to get rid of the negative. How can I make the following thing right? So I want to not have that negative, and I want to write logarithm of x over x. And how can I make that right? How do I spend that negative? Yeah, we'll switch the order of evaluation. Switching the order of evaluation, in a sense, spins that negative. So I find it that seems to help. Finally, for that one, so we can evaluate that, this will be what? The logarithm of 1 over 1 minus the logarithm of e over e, and then plus the antiderivative of that, that would be x to negative 1 over negative 1, and then this evaluated from 1 to e. So what's the logarithm of 1? Zero. What's the logarithm of e? 1. And then I'm going to spend that negative by flipping those also. So then this will be plus 1 over x from e to 1, like so. Okay, so then this will be negative 1 over e, and then plus 1 over 1 minus 1 over e. And then simplifying that, that'd be 1 minus 2 over e. Beautiful. The arithmetic was mildly interesting, which is why I took the time to do it kind of carefully. Because usually I just kind of just say, because it's usually boring. Good. Any question about this one? Okay. So I think it's probably time for a quiz, nearly, unless there's any questions.
Did you grow up on a farm?
Well, not exactly. It's more like I'm like one generation removed. So like I didn't grow up on it, but I spent a lot of time. And I'm the only one that's like that's a math person, you know. So like when I go and visit them, you know, they'll ask me questions like, you know, they'll say, okay, what's 4,368,9 times blah blah blah, and you know, just rattle off some other number. You know, I'm like, I have no idea. Why would I know that? You know, but you know, they know that I don't know it. They just, you know, give me a hard time.
Which state was it from?
We're all from Texas.
Oh.
I mean, the recent generations are anyhow.
You ever write stuff out like this form is showing?
I used to, but it's not worth it anymore, you know, because they're, you know, that plays into their hand, right? The whole point, the whole point is for them to cause me grief. Okay, so no other questions? All right. Till 45.